Dear students, now let us see the concept of rotational kinetic energy. So, this is a rigid body which is rotating around this axis with an angular velocity of omega. So, this rigid body, it is a combination of many particles, so millions and millions of particles will be present in this rigid body. So, we will take some such particles. So, let it be a small particle of mass m1, and this is a small particle of mass m2, and let it be another small particle of mass m3. So from the axis it is moving with a velocity of v1 at a distance of r1. So this mass m2, which is at a distance of r2, it is traveling with a velocity of v2, and this m3, which is at a distance of r3, it is traveling with a velocity of v3. Then total rotational kinetic energy can be written as K is equals to, now if I add the sum of the kinetic energies of all these particles, let us see what we will get. So half into m1 into v1 square plus half into m2 into v2 square plus half into m3 into v3 square. So it goes on for the remaining number of particles. So K is equals to, so half into, so now if I study V, so already we have discussed that V is nothing but tangential velocity, which is equals to omega into R. So as this rigid body, it is having an angular velocity of omega, every particle will be having an angular velocity of omega itself, but the tangential velocity of each particle will change because tangential velocity is directly proportional to radius. So therefore, instead of v1 for the first particle, which is at a distance of r1, I can write half m1 into I can write omega into r1 square, which is at a distance of r1. For the second particle, half m2 into, instead of v2, I will write omega into r2. So this is whole square, this is whole square, and this goes on. So like this, K is equals to, now if I see the terms which are common, half and omega square are common. So if I take them common, half into omega square into m1 r1 square plus m2 r2 square plus dash dash dash, this goes on to the total number of particles. Now if I see this m1 r1 square and m2 r2 square, so they are nothing but moment of inertia of individual particles around this axis of rotation. So if I add the moment of inertias of all these particles, definitely I can say I will get the total moment of inertia of this total rigid body around this axis. So therefore I can write K is equals to half omega square into I. So therefore the equation becomes half into I axis into omega square. So kinetic energy is equals to half I omega square. So this is the total kinetic energy possessed by this rigid body because of rotation around this axis. So therefore K is equals to half I axis into omega square. Now if I study a situation like this, for example, if I take a disk, for this disk, if it is rotating around this central axis, so that is axis is present on the center of mass itself, and this disk is rotating with an angular velocity of omega, then I can say that this disk has only rotational kinetic energy, and that rotational kinetic energy I can write it as Kr is equals to half I center of mass into omega square. So this is how I can write. Now similarly, if this disk is having a translational velocity also, that is this disk, it is rotating around this axis with an angular velocity of omega. Similarly, center of mass is also translating with a velocity of v center of mass also. Then in this condition, this disk I can say it has two energies. One energy is kinetic energy of rotation, and another energy is kinetic energy due to velocity of a center of mass also. Then in this condition, total kinetic energy can be written as K, total kinetic energy can be written as kinetic energy due to rotation plus kinetic energy due to translation. This is how I can write. So therefore, I can write K total is equals to K rotation. Due to rotation, the kinetic energy is half I center of mass into omega square plus K translation can be written as half into m into V center of mass square. So this is the relation for total kinetic energy. If I consider that this disk is having both the energies, so it is rotating around this axis. Similarly, it is translating with the center of mass having a velocity of Vcm. So K total is equals to half into I center of mass into omega square plus half into V center of mass square. Now if I consider this situation, now if I consider that, now if I take axis here, if I consider that this is an axis which is perpendicular to the plane of this paper, and this disk is rotating with an angular velocity of omega around this disk. Now how can I consider? So can I consider the same equation, or can I consider the different condition that we will discuss? So here also this disk is having an angular velocity of omega square. Similarly, if I take a center of mass of this disk, then this center of mass is also having a velocity of V center of mass, which is indicated by this one, V center of mass. So again, if I add these two energies, so that should give the total kinetic energy possessed by this body. This is solving by one method. So let us see, here I can write K total is equals to half I center of mass into omega square plus half into m into V center of mass square. So K total can be written as half into, so I center of mass into omega square plus half into m into V center of mass. V center of mass is at a distance of r here. So therefore, if this disk is rotating around this axis, then here this velocity will become tangential velocity to this axis of rotation, which we have already discussed. And equation for tangential velocity is equals to omega into r, where r is the distance of the point where we are checking the tangential velocity from the axis of rotation. So from this axis of rotation up to this point, the distance is r radius itself. So instead of Vcm square, I will substitute omega into r whole square. Now if I calculate this value, then half into omega square, they are constants. I will take them outside. So half into omega square into, now which are the terms which are left behind? So I center of mass plus, now half omega square, they are taken outside. So m into r square. So this is the relation which I got. So this is nothing but I center of mass plus mr square is just looking like a parallel axis theorem. So I center of mass is the moment of inertia when axis is present here. Now when axis is present here, then by parallel axis theorem we will write I is equals to I center of mass plus md square. So here d is the distance between these two axes. So total kinetic energy is half into omega square into I center of mass plus mr square. So what we understand by this experiment, by this calculation, we have understood that if I can calculate the total kinetic energy about the axis about which this body is rotating, then that will give the total kinetic energy of this body. Total kinetic energy in the sense the sum of translational kinetic energies plus rotational kinetic energies. So therefore, K total can also be written as half into I axis into omega square. So I axis indicates the moment of inertia around that axis around which the body is traveling. Or if I want to write separately, then I can write like this also, half into I center of mass into omega square plus half m into V center of mass square. So this is by considering only rotational motion of the body. This is by considering only translational motion of the body. So this energy is K rotation and this energy is K translation. Whereas this energy is the sum of K rotation plus K translation combinedly. So this is how we can calculate rotational kinetic energies of the bodies. Therefore, this combined motion can be written like this also. So this motion, which is rotating around this axis with an angular velocity of omega, so it can be split into two types of motions. One is the motion around the center of mass with an angular velocity of omega, and the disk traveling translationally with a velocity of v center of mass. So either directly I can use relation for total kinetic energy by considering axis here, or individually I can add rotational kinetic energy and translational kinetic energy. Then also I will get the total kinetic energy of this body. So based on this discussion, let us do some examples so that we can understand the concept clearly. So now let us see this question. So a composite rod is made to rotate with an angular velocity omega. So here around this axis, this is a composite rod which is attached. So here the length of this light rod is L. Light rod means the mass of this rod we are neglecting. And attached to this one there is another rod whose mass is M and whose length is L in this condition. So this composite rod is rotating around this axis with an angular velocity of omega. Then we are supposed to find out these values: translational kinetic energy, rotational kinetic energy, and total energy. So let us see how we can do the first one. So we know that translational kinetic energy is nothing but half m into v center of mass square. Now what is the velocity of center of mass, that we will calculate. So let us see this one. So velocity of center of mass first we will calculate. To this rod, center of mass is exactly located at its center. So this is the position of center of mass. But what about velocity of this center of mass? So if this is the axis of my rotation, then this velocity of center of mass will become the tangential velocity of this rod at this point. And we know that tangential velocity already we have written in equation previously. V tangential velocity is equals to omega into r, where r is the distance from the axis of rotation. So here this center of mass is at a distance of L plus L by 2. L is the length of the rod, and in the second rod it is at a distance of half of the length of it, which is called L by 2. So therefore V tangential is equals to V center of mass is equals to omega into, instead of r I will write L plus L by 2. So therefore V center of mass is equals to omega into 3L divided by 2. Now if I substitute in translational kinetic energy, so this is equals to half into m into, instead of V cm square I will write omega into 3L by 2 whole square. So therefore half into m into omega square into 9L square divided by 4. So therefore 4 2s are 8 here. So 9 by 8 m omega square L square. So this is the translational kinetic energy of this total composite rod. Now second one, we are supposed to find out rotational kinetic energy. So if I want only rotational kinetic energy, then the equation is half I center of mass into omega square. So therefore half into, so now I am considering this rod to be rotating only around its center of mass with an angular velocity of omega, then I will get only rotational kinetic energy. Now we know that the moment of inertia across the center of mass of a rod is nothing but ml square divided by 12. So therefore I is equals to ml square divided by 12 into omega square. So therefore this is equals to ml square omega square divided by 24. So this is our answer. Now if I calculate the total energy of this rod, which is our answer for the third one. Let us see how we can calculate. So total energy is nothing but translational kinetic energy plus rotational kinetic energy. So 9 by 8 m omega square L square plus ml square omega square divided by 24. So if I take LCM of this one, then 24 I can take. So 8 3s are 27 m L square omega square plus ml square omega square. So this is nothing but 28 m L square omega square divided by 24. So if I do this calculation, then it should be equal to 7 by 6 m L square into omega square. So this is the answer which I will get for total kinetic energy of this rod. Now let us see in second method how can I calculate the total kinetic energy of this rod. In second method, total kinetic energy can be calculated by considering the axis to be present at the original axis. So around this axis, now I will calculate the total kinetic energy of this rod. It means that if I take this axis as my rotation, then moment of inertia also I have to consider at this axis. Then it means the total body, it is rotating around this axis with an angular velocity of omega. Now k total is equals to I half into I axis into omega square. Now how can I calculate moment of inertia around this axis? So I can use parallel axis theorem. For this rod, when axis is present on the center of mass, we know the moment of inertia is ICM. Now our axis is present at a distance of L plus L by 2, 3L by 2. So I axis is equals to I center of mass plus md square, where d value is 3L by 2. So therefore I will write I axis is equals to I center of mass is ml square divided by 12 for a rod when axis is present on the center of mass plus m into, now distance between these two axes is equals to 3L by 2 into whole square. So therefore I axis can be written as, so this is ml square by 12 plus 9 ml square divided by 4. So I axis is equals to, now if I take LCM to be 12, then it is ml square plus 3s are 27 ml square. So which is equals to 28 ml square divided by 12. So if I do this calculation, then it is 14 ml square divided by 6. Further I can do this calculation, then it will become 7 ml square divided by 3. So up to here I will get the answer. Now if I substitute in this relation, then k total can be written as, so half into I axis is 7 ml square by 3 into omega square. So 3 2s are 6, so which is equals to 7 by 6 ml square into omega square. Now if I observe this result and this result, they are exactly equal. So it means that instead of considering the translational energy and rotational kinetic energy individually, if I take moment of inertia about that axis actually through which this composite rod is rotating, then I will get total kinetic energy by bypassing one more step. So directly I can get total kinetic energy. Dear students, now let us see this question. So this is a rod of mass m and length L, so which is traveling, which is rotating with an angular velocity of omega is equals to root g by L. Then we are supposed to find out its rotational kinetic energy of translation and total kinetic energy. So let us see how we can calculate. First one, rotational kinetic energy. So rotational kinetic energy, already we have discussed the equation. So half into I center of mass into omega square if I consider only rotational kinetic energy. And I center of mass is nothing but ml square by 12 if axis is present for the rod exactly on the center of mass. So k rotation is equals to half into I center of mass is ml square by 12 into and omega. So square root of g by L whole square. So this is equals to half into ml square by 12 into G by L. So therefore this square and L gets cancelled. So mgl divided by 24. So this is our equation for rotational kinetic energy. Now let us see the second question, kinetic energy of translation. So kinetic energy of translation also we have studied equation. So K translation is equals to half into m into v center of mass square. Now here this is the velocity of center of mass, and this velocity of center of mass is nothing but a tangential velocity at this distance of L by 2 from the axis of rotation. So V tangential is equals to V center of mass is equals to omega into r, where r is the distance of this point from the axis of rotation. So from the axis of rotation this distance is L by 2, so omega into L by 2. So this is our velocity of center of mass. Now if I substitute in this relation, K translational is equals to half into m into, instead of VCM I will write omega into L by 2 into whole square. So therefore half into m into omega square into L square divided by 4. So the answer which we will get is m omega square L square divided by 8. So this is our translational kinetic energy. Now he is asking the third question also, which is called total kinetic energy. So K total is equals to K translational plus K rotational. So if I add both these energies, then it is equals to this one also. Further we can simplify this one. We forgot simplifying this one. So m by 8 into L square into, instead of omega we can write G by L. So G by L. So this is mgl divided by 8. Now if I add these two, then it is equals to translational kinetic energy is mgl divided by 8 and rotational kinetic energy is mgl divided by 24. Now if I take their LCM 24, so this is 3 mgl plus mgl. So therefore it is equals to 4 mgl divided by 24, which is equals to mgl divided by 6. So this is the answer for total kinetic energy. Now let us see how we can calculate total kinetic energy by using the second method, which we have already discussed. Now instead of considering rotational and translational kinetic energy separately, if I consider the moment of inertia across this axis, then it means across this axis this total body is rotating. So therefore the total kinetic energy can be written as, so half into I axis into omega square. Now how can I calculate this moment of inertia across this axis? Moment of inertia across any end of a rod is nothing but ml square divided by 3, which we have studied in the concept of moment of inertia. Now if I substitute in this equation, so K total is equals to half into moment of inertia across this axis, that is one end of the rod, it is ml square by 3 into omega square, nothing but G by L. So again I got, so L and square gets cancelled, so mgl divided by 6. So this is the second method of solving this problem. So here also we got mgl by 6, here also we got mgl divided by. Now let us see this question. So this is a composite rod. So one rod is having a mass of m and length L. So another rod is having a mass of 2m and its length is also L here. So around this axis, this composite rod is rotating with an angular velocity of 10 radians per second, and m value is 1 kg, that is this rod is having a mass of 1 kg, then this rod will have a mass of 2 kgs. Then find the kinetic energy of rotating composite rod. So here we are supposed to find out kinetic energy in the sense total kinetic energy that already we have discussed. So if he asking kinetic energy, then it means that it is the sum of translational kinetic energy plus rotational kinetic energy. So if I want to find out a total kinetic energy, that is the sum of translational as well as rotational, then I will take the axis as the original axis of rotation instead of taking axis around the center of mass. So if I take axis here, which is the actual axis of rotation for these two rods, then definitely I will get directly the total kinetic energy, which is called rotational kinetic energy, or we can say total kinetic energy of this composite rod. So therefore, if I do this calculation, so kinetic energy total can be written as half into I axis into omega square. Now the question is, how can I calculate I axis, moment of inertia around the axis of rotation? This I can write, it is equals to I1 plus I2. So moment of inertia of first rod around this axis and moment of inertia of second rod around the same axis. So therefore this I can write, for the first rod moment of inertia I can calculate very simply, because for the first rod axis is present at the edge of the rod, and for such situations we know already that moment of inertia can be written as ml square divided by 3. Now if I take I2, that is moment of inertia for the second rod, for here I have to use the parallel axis theorem. For the second rod, this is the center of mass, and around the center of mass moment of inertia is ml square by 12. But from this axis, the original axis of rotation is at a distance of L plus L by 2. So this distance will become L by 2, and this distance is already given as L. So the new axis of rotation is at a distance of L plus L by 2, which is equals to 3L by 2. So therefore total moment of inertia for the second rod can be written as 2m, because its mass is 2m, 2m L square by 12 plus, so already we have studied parallel axis theorem, I is equals to I center of mass plus md square. So therefore instead of m I will write 2m and d square. What is d in this condition? Distance between two axes. So distance between two axes is L plus L by 2, which is called 3L divided by 2 whole square. So this is the moment of inertia of both the rods around the axis of rotation around this axis. Now if I do all this calculation, then I will get I axis is equals to 5 ml square. This is the result which we get. Now directly if I substitute in the given equation, then I can write total kinetic energy is equals to half into I axis into omega square. So half into I axis value is 5 ml square into omega square. So this should be equal to, so half into 5 into mass is given as 1 kg here. So 1 into length of each rod is L is equals to 1 meter, which is given. So 1 square. So I think here length is not given. Length is equals to 1 meter. So 5 into m into L square into omega square. So angular velocity is given as 10 square. So this is equals to 500 divided by 2, which is equals to 250. Let us see this question. A uniform disc of mass m is fitted with a rod of mass m by 2. If the bottom of the rod is pulled with a velocity v, it moves without changing its angle of orientation, and the disc rolls without sliding. Find the kinetic energy of the system. So this is a disc to which we are attaching a rod of mass m by 2, and this m by 2 it is moved with a linear velocity of v here. Then along with this rod, this disc also moves in the same direction without slipping. Then the question is, what is the total kinetic energy of this system? System means here kinetic energy of rod plus kinetic energy of this disc. So let us see how we can do this question. So total kinetic energy is equals to kinetic energy because of this rod and kinetic energy of this, total kinetic energy of this disc. Now what about total kinetic energy of the disc in this condition? So disc is rolling in this condition. It means it is having rotational motion as well as its center of mass also it is traveling with a velocity of v in this condition. So therefore total kinetic energy can be written as kinetic energy of the disc is equals to translational kinetic energy plus rotational kinetic energy. Translational kinetic energy, we know it is half into m into v center of mass square plus rotational kinetic energy is equals to half into I center of mass into omega square. And kinetic energy of the rod is equals to half into mass is m by 2 and it is moving with a velocity of v, so v square. So half m by 2 into v square in this condition. Now, instead of calculating the total kinetic energy of the disk separately by considering translational kinetic energy and rotational kinetic energy, so total kinetic energy I can calculate if I can calculate this disk is actually rotating around which axis. So this disk, it is rotating around this axis, which is called the temporary axis of rotation, or we can call it as the instantaneous axis of rotation. So this total disk, if you remove this total ground and this total ground, so it is analogous to that this disk is rotating around this point. So it is rotating like this. So this will become my temporary axis of rotation, this point P, or I can call it as the instantaneous axis of rotation. So around this axis, if I can calculate moment of inertia, then directly I will get the total kinetic energy of the disk. So therefore, total kinetic energy of the disk can also be calculated like this. So half into I axis into omega square. So I axis means this is the axis around which this disk is rotating temporarily. So therefore, how can I calculate this I axis? So on the center of mass, the moment of inertia is half mr square. And here there is one axis, here there is another axis. So both the axes are parallel and they are separated by a distance of r. So I will use the parallel axis theorem. I is equals to I center of mass plus md square. So m into d is the distance between the two axes, which is called r here. So r square. So I axis will become 3 by 2 mr square. So this is the total moment of inertia of this disk around this axis. Now if I substitute in this relation, so therefore kinetic energy of the disk is equals to half into I axis is 3 by 2 mr square into omega square, which is equals to 3 by 4 mr square into omega square. Now if I calculate the total kinetic energy of this system, so K is equals to kinetic energy of the rod is half into m by 2 into v square plus this kinetic energy of the disk is 3 by 4 mr square into omega square. So K is equals to mv square by 4 plus 3 by 4 mr square into omega. So this rod is having an angular velocity of omega. Omega can be written as v by r into whole square. So therefore kinetic energy can be written as, so here r square and r square gets cancelled. So mv square by 4 plus 3 by 4 mv square. So total answer is mv square. So this is the total kinetic energy of this system. Now let us see this question. So these are two masses m and m which are connected by light rods. So they are light rods. And these two rods, that is these two masses, they are rotating around this axis, and length of each rod is L and L, and the endmost mass, it is moving with a tangential velocity of v. Then we are supposed to find out the ratio of translational and rotational kinetic energies. So here we should be careful that he is not asking about total energy. So total energy of the rod is the sum of translational and rotational kinetic energies. But here he is asking only the ratio of translational energy to the energy of rotational kinetic energy. So already we have studied equations of this translational and rotational kinetic energies. So K translational is equals to half into m into v center of mass square. So this already we have studied. So for these two masses, definitely we can say their center of mass exactly lies at the center. So at a distance of L by 2 and L by 2 from both these masses. So therefore half into m into velocity of center of mass. Now what about velocity of center of mass? For example, this is a rod of total length 2L. So endmost point has a length of v. Then the middle point will have a velocity of v by 2, and this point, which is again in the middle of v by 2 and v, this will have a velocity of 3v divided by 4. So like that we can calculate velocity in this condition, or just let us draw a diagram. So if this is the total length of the rod, and if this is the axis of rotation, so this one is having a velocity of v, which is the total length of the rod. Then at the middle it should have a velocity of v by 2. At 1/4 of the length it should have a velocity of v by 4. Then here at 3/4 of the length it should have a velocity of 3v divided by 4 in this condition. Or always we can calculate by using v is equals to omega into r. So angular velocity is not given, so first of all we can calculate angular velocity, and up to here the distance is 3l by 4, and by multiplying that then also we can calculate this velocity, which is the tangential velocity of this rod. So therefore now if I substitute in this equation, for these two masses, center of mass is existing here, which is traveling with a tangential velocity of 3v divided by 4. So therefore k translational can be written as half into total masses, or two masses are there, so 2m, and velocity of center of mass is 3v divided by 4 whole square. So 2 and 2 gets cancelled, so m into 9v square divided by 16, or 9 by 16 mv square is the translational kinetic energy of this rod. Similarly, now we are supposed to find out rotational kinetic energy also. So rotational kinetic energy is half into I center of mass into omega square. Now what about center of mass of this rod? Center of mass is existing at a distance of exactly at the middle, that is at a distance of 3l by 4 from the axis, and for these two masses it is at a distance of l by 2 and l by 2. So therefore I center of mass for these two bodies, that is moment of inertia across the center of mass, for both the bodies can be written as m into l by 2 whole square for one body, and for another body it is also equals to ml by 2 whole square, because this distance and this distance, which is equals to l by 2. So therefore if I calculate total moment of inertia, then it should be equal to ml square by 4 plus ml square divided by 4, so which is equals to ml square divided by 2. Now if I substitute in this rotational kinetic energy, so k rotational is equals to, so half into I center of mass is ml square by 2, and omega can be written as, so v by r, so we know v is equals to omega into r, so omega is equals to v by r, so v by, so this end point is having a velocity of v at a distance of l plus l, 2l from the axis. So here r value will become 2l, so v by 2l into whole square. So this is equals to half ml square by 2 into v square by 4l square. So 4 2s are 8, 8 2s are 16. So therefore this is the l square and l square gets cancelled. So mv square divided by 16. So this is the rotational kinetic energy of this rod. So he is asking k translational divided by k rotational. So 9 by 16 mv square divided by mv square divided by 16. So therefore all these values get cancelled. So 9:1 is our answer. Dear students, now let us see this question. A uniform sphere of mass m and radius r rolls without sliding over a horizontal plane, rotating about a horizontal axis OA. The center of sphere moves with a velocity of v along a circle of radius capital R. Then find the kinetic energy of the sphere. So this is a sphere which is moving on a horizontal circle. So it is having a radius of small r, and it is rotating in a table of radius capital R. So it is rotating around this axis, it is spinning around this axis OA in this condition. Then we are supposed to find out the total kinetic energy of this sphere. So here I can say this sphere is having three types of energies. So total kinetic energy can be written as kinetic energy due to translation, because center of mass of the sphere is also having particular velocity of v, and kinetic energy of rotation because it is rotating around this axis, plus kinetic energy due to spinning also. So now instead of these three energies, simply I can write K total is equals to kinetic energy around the axis around which it is rotating plus kinetic energy due to spinning. So what is the meaning of this one? This already we have studied. Instead of two energies separately, if I take the original axis around which body is rotating, then directly I can get the total kinetic energy of this body. So this k axis can also be written as k orbital also. So kinetic energy of orbitation plus kinetic energy of spinning. Now let us see how I can calculate kinetic energy due to orbitation. So this I will write half into I axis into omega 1 square. So how can I write I axis? So this I can write I center of mass plus md square by using the parallel axis theorem. So around the center of mass, this sphere will have a moment of inertia of 2 by 5 mr square, but the original axis is present here around which the sphere is rotating with such a distance of capital R. So in this condition, d will become capital R. So m capital R square. So next angular velocity omega 1. So this last point or end point of this axis, it is having a velocity of v, and this tangential velocity is at a distance of capital R. Then omega 1 can be written as v by r. So therefore total orbital kinetic energy can be written as, so half into, instead of I axis I can write 2 by 5 mr square plus m capital R square into omega 1, which is called v by r whole square. Similarly, I have kinetic energy due to spinning also. Now this sphere, it is rotating around its own axis around the center of mass. So therefore I can write half into I center of mass into omega 2 square. So I center of mass is equals to 2 by 5 m small r square, because small r is the radius of this sphere, and omega 2 can be written as v by small r. So therefore k spinning is equals to, so half into 2 by 5 m small r square into v by small r into whole square. Now if I add both the energies, then I can get a k total is equals to k orbitation plus k spinning. So if I add these two energies and this energy, then the answer which I should get is 7 mv square divided by 10 into 1 plus 2r square divided by 7 capital R square. So I hope you can add these two and you can get this result. So now let us see this question. So this is a rod which is present on a horizontal plane, and its ends are having velocities of 2v and v. So these are the velocities which we are giving to the ends of these rods. So nothing but they behave like tangential velocities to these rods. Then we are supposed to find out the angular velocity of the rod, linear velocity and kinetic energy of the rod. So the question is, why linear velocity is produced in this rod? So linear velocity is produced because these forces are unbalanced forces, or I can say if these velocities are not equal, then it means that definitely center of mass also will have a velocity which we can call it a velocity of center of mass. So because of these unbalanced forces or unequal velocities, center of mass also will have a translational velocity which we can call it as velocity of center of mass. Now how can I calculate these quantities, angular velocity, linear velocity and kinetic energy of this rod. So here we have two unknown quantities. Angular velocity of the rod is an unknown quantity. Linear velocity of the rod is also an unknown quantity. So therefore we will try to write two equations because two unknown quantities are present here. So how can I write two equations? So in kinematics already we have studied how to write relative velocity equations. For example, this is velocity of point A, which I call it as VA. So therefore I can write VA dash is equals to VAC dash plus VC dash. This is how I can write. So velocity of A with respect to C plus velocity of center of mass. So this point will have two velocities, velocity with respect to the point of rotation and velocity with respect to similarly it have velocity of center of mass also. Or you can always write this one like this. VAC can be written as VA dash minus VC dash plus VC dash. So plus VT dash minus VC dash gets cancelled. So again I will get VA dash is equals to VA dash. So this is how we have studied the concept of relative velocity. So with the help of this concept, let us see how I can write the equation for point A here. So VA, I will write it this direction to be negative, its velocity is minus V, and velocity of A with respect to C, I can write, because this is a tangential velocity, we have a formula, V is equals to omega into R. R is the distance from the point which we are considering. So from the center of mass, this point has a distance of L by 2 because this total length is L and this length will become L by 2. So therefore VAC can be written as L by 2 into omega. V is equals to omega into R. So L by 2 into omega. Now the question is, here we are writing VAC in the form of vectors. So therefore is it a positive value or negative value? So definitely if I see with respect to the angle of omega also, rotation is in this direction. So angular velocity is perpendicular and inside this paper. So that direction I can take negative. Or VAC means, it means that this point will be going into rest position. That is velocity of second point always will be in rest position. That is what we have studied in kinematics. So relative to this position, this point A is moving in this direction and that direction already we have considered negative. So minus L by 2 into omega plus VC. And velocity of center of mass will be in this direction, because this is a greater velocity when compared to V here. So I will write VC. So this is my equation number 1. Similarly, how can I write equation for this point B here? I can write VB dash is equals to VB with respect to C plus VC dash. So again I can write like this. So now VB dash I can write to 2V because this direction I am taking positive. And velocity of B with respect to C, again by considering V is equals to omega into R, I can write L by 2 into omega. Now if this direction is negative, this direction will be positive. So positive L by 2 into omega plus velocity of center of mass is VC. So this is my equation number 2. So if I add these two equations, let us see what I will get. Minus C plus 2V is equals to L by 2 into omega minus L by 2 into omega gets cancelled. So I will get 2VC. So therefore plus V is equals to 2 into VC. So therefore I will get VC is equals to V by 2. And this is my answer for the second question. So velocity of center of mass of the rod or linear velocity of the rod is V by 2. Now take this V by 2 and substitute in any one of these equations. I will get the value for omega also. So I will write 2V is equals to L by 2 into omega plus VC value is V by 2. So therefore if I solve this equation, then I will get omega is equals to 3V divided by L. So VC is equals to V by 2, omega is equals to 3V divided by L. So this is my answer for the first question. Now let us see how we can solve kinetic energy of rod. So total kinetic energy we know already, we have discussed about this one. It is the sum of translational kinetic energy plus rotational kinetic energy. So translational kinetic energy equation also we have discussed. So half into V center of mass into omega square plus rotational kinetic energy is half into I center of mass into omega square. So, this is half mv square. So, half m into v square. Now, if I substitute all these values, then I can write half into velocity of center of mass, just we have calculated it is v by 2 into whole square into m plus half into I center of mass is, because this is a rod, the equation will be ml square by 12 into omega. Omega value is 3v divided by L whole square. So if I do this calculation, I will get total kinetic energy is equals to mv square divided by 2. So this is my answer.